If anyone of our audience from CUSAT is still interested in joining, please register through our link. The topic of today's webinar is System Design for Mission 100K Feet Payload. I'd like to introduce today's presenter, Timothy Simon Thomas, third year Electronics and Communication Engineering student at School of Engineering CUSAT. He is the Mission Director of Mission 100K Feet, a unique venture to send and retrieve high-altitude payloads launched for upper atmospheric research. He is also the founder and CEO of Sense Space Innovation, a startup incubated at CITIC at CUSAT. He has done his summer internship at IIT Guwahati on VLSI design and implementation. He is the Vice President of at IEEE, Innovation Research and Exploration of Space at CUSAT. And of course, he's a good public speaker. Okay, just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the comment box in your control panel. I'll bring them up during the presentation, and we will also have time for questions at the end. And please be sure to keep your mics off during the presentation. Now, without further ado, I'll hand over to Timothy.
Hi everyone, am I audible? I hope I'm audible. Okay, so that was a really well-written intro. So that is interesting. So let's get into the topic today. So I'm really excited about today's presentation, and I'm more nervous because I have really high-profile people as my audience, and I'm not at all, the kind of person to do such a thing. So anyway, with what we have, let's just dive right in. So I'm just opening my PowerPoint. Just bear with me for a moment. So you guys, so I'm not sure whether, is the screen visible? Could somebody just respond just before we start off? So I'm just going to start off. So Mission Feet, this was a really amazing journey we had. So I just want to give you a few glimpses of what it was like to be a part of this amazing team, this amazing family, and is now only known as Mission 100K Feet, right? So let's dive right in. So this was the control station, our control room for the launch, and this is just on the snap. And now this is a sneak peek at our final launch, right? So I'm sure many of you don't know what Mission 100K Feet is. I'm talking about those from outside the set, in case there are people like that, right? So this is what you see here is the Kochi coastline. So, so the Kochi coastline is clearly visible in this picture. So let's just go in. So the story of a long journey over 6 months started here. What is this fascinating building? This is ACAR, the Advanced Center for Atmospheric Radar Research. I'm hearing that I'm not audible. Am I audible? Could somebody please confirm? Okay. The journey right at ACAR. So the journey began with ACAR. So ACAR is the Advanced Center for Atmospheric. So they do a lot of cutting edge technology, and we are actually privileged to be CUSATians who have this facility, right? So let's just go. So it all started here, right? Why do I say so? So I say so because, so you can see me standing right here. So this is our first year batch, right? So we are all here for the first time witnessing a radio sonde launch, right? So this is at ACAR, and you can notice we are all first years because we are all wearing badges, which is an uncommon sight today, right? So this was where we first came to know, like, there's a device called a radio sonde that is going to be launched using a weather balloon. So let's see. So, see, I want to start off by saying that Mission 100K Feet is a team effort. We had an enormous team that did a lot of work in the background to make this thing happen. So I just want to start off with a disclaimer. I want to say that all things that we're discussing here today are, things that solutions we found out. They are not really to the best way to, they're not optimal in the sense of the word, right? So what we are trying to do is have a set of solutions and try and find innovative solutions, which may be naive since we have a really short time. So I just want to share our journey with you. So let's begin. So let's start off with what is radio sonde thing, right? Funny word. So radio sonde, as the word should suggest, is radio and sonde. It means it's a device. Sonde is in some language means to sound, right? To sound meaning to return data, right? It's going to send you something. So that's basically what this radio sonde is. Using radio frequency, we are going to this data. Where is this going to be used? So this kind of stuff is used in atmospheric radar research, right? Atmospheric research. So it is going to collect data from the atmosphere, and it's going to send it back to the ground station. So that's the ground station right here, and we have a payload that is usually on a balloon that is sent up, and it sends this data back down, right? You have sensors that send it back down. So without further ado, let's move on. So this is the picture of the infamous radar. If it's coming across, you can see the ACAR at the top right hand side, and you can see a lady dressed in red on the bottom hand side. Yeah, and she's also holding a radio sonde. So you might be thinking, what does a radio sonde, a device which measures atmospheric data, doing with the radar, right? So let's come to why this radar was built. So this radar was built with the concept, with the idea of using it to get meteorological data without sending a balloon. So then you ask, why a radio sonde? If you are able to get the same data using a radar, why are you opting for a radio sonde? So the answer lies in the figure at the left. So this is from a research paper that was published from ACAR, right? So what this is basically a plot. So you can see a neat marking here that shows, radar and radio sonde. So radio sonde, that is the data from the radio sonde in red and the data from the radar in blue, right? So before you guys get bored up, I just want to say all the radio sonding was used for is to find out how we can, validate this radar. Like, this radar is cutting edge technology. It's the first radar in the world to operate at 205 megahertz. So let's not go into that. So they wanted to validate it. So that is why a radio sonde was used. Now, I would also like to add that radio sondes are expendable, meaning they can't be reused. Now, that's a drawback. So the other thing is radio sondes are expensive. So you have a device that's really expensive and you're not going to get it back. It's one-time use, right? So from this launch we wanted to try and reuse this thing, right? How can we make a radio sonde reusable? So let's start off. So the thinking process, radio sondes are expensive, we need to get them back, right? So the target, we need to carry a radio sonde to 100,000 feet. The next thing, we need to come back with this radio 100,000 feet. So let's see what we need here, right? So we need some sort of vehicle which is going to carry us there, right? So we have to go to 100,000 feet. We could use rockets, we could use aircraft, things like that, and we need something to come back. Something like, say, the NASA space shuttle to come back, right? You use a rocket to go up, you need to come back. So that's the basic thinking of it. And we need something to carry. So what is that something? It should be pretty clear now. It's nothing but the radio sonde, right? So let's just dive in. So this was the starting idea. I hope the image is loaded. What you see is two balloons carrying an aircraft. You know, there are some things you aim really high and often don't reach those aspirations. This is one of those things, right? So we send up this vehicle, anticipating that it comes back with the radio sonde. Right. So what you see here is the radio sonde itself, right? So it is carefully attached to the payload meaning the aircraft, and is going to be sent up. So that's how we basically, the idea was really far-fetched, and I still believe it's possible, but requires a lot of effort. So we were trying to bring back this vehicle with the radio sonde all the way from 100,000 feet. So this was our final PRV, and this never had the yogam to fly, right? So we were not able to complete it in the time. So this was all about a guided system. Then we thought, why not use an unguided system wherein we can bring back these payloads, right? Without a guided system. Like, why go for this extravagance of having an aircraft flying back to you? Why not just make the small system? So what we did was, we wanted a parachute, right? We had a parachute with just the payload being the radio sonde, right? So we also needed a method wherein we could, get data as to where this payload was, where this radio sonde was to retrieve. So that's the mission. What's our mission now? We no longer have a guided system. The system plans to send something, get its coordinates, go and find it. The thing is that thing should come back safely. So this was what we were doing till then. Then suddenly everything changed. We were going to wind up. So this was just an amazing opportunity, Like we're sitting here thinking of launching a weather balloon to space, and all of a sudden we have this solar eclipse taking place in our state, in Kerala, and it is going through Wayanad. And all of a sudden, we have the equipment to capture this from the sky. So if you're like me, you're really excited, right? You really want to know what it looks like to see a solar eclipse from near space, right? So I'm not sure the animation is playing out well. So this is where you see the red region. So that's where the solar eclipse was going through, right? So we were going there. And why were we going there? Well, we wanted to capture these scenic shots. Well, this is nothing but the shadow of the moon moving off the surface of the earth. So let's move on. So we finally pack our bags. The payload's all ready. Our cars are packed, and we're ready to go. And we are at the site. We are all really excited. This is our first time we are doing something like this. And there are a few hiccups here. I'll get to that in a moment. So you can see the payload all handsomely packed up, and our team is ready and ready for the launch, right? And what did we get? Well, nobody saw a shadow. We didn't get the footage we were after. But was this mission unmotivated? I wouldn't say so. Why? So basically, this mission posed a lot of new ideas. Like, for instance, we could no longer use the radio sonde. As you would know, the radio sonde was the primary reason why we were launching, right? Why couldn't we use the radio sonde, you ask? Well, as you would have seen, the radio sonde requires a ground station where you can receive this data. And our ground station is in Kochi, and the receiver is not portable, right? So the radio sonde is transmitting data, and the receiver is not portable. So that's a big bump. So basically, we had to design our own radio sonde or something that does the job, right? So let's get into the design process. So this was how we found the payload and all things like that. So I want to discuss this in a story-like manner. And so this is an amazing group of people, right? We go find something in the midst of forest. So that was all well and good. So I just want to ask a question. So instead of me doing all the talking, I would like you guys to use the chat box. First one to answer wins nothing, right? So you see many crescent-shaped pictures. So this shot was taken by our team, mainly by Srikant. So I believe he's also part of this. And why are there crescent shapes in the shadow during the solar eclipse? At the very top, you can see the sun, as the moon covering the sun. And at the bottom, you can see something weird happening with the shadows, right? So anybody quickly answering me? So as to why, yeah, exactly, the pinhole effect. I believe you were there for the another session. Yeah, the pinhole effect. So the pinhole effect is basically you're getting an image. So I'm sure if you don't know what the pinhole effect is, please Google it. So the pinhole effect gets the image of an object at infinity, and here the object being the sun. So this is a good way to observe a solar eclipse without looking at the sun, but rather its shadow, right? So this everything went well. We got the payload back where in the midst of the forest, right? So we had to go trekking. It was a wonderful experience. I'm sure our team would say so. We had an amazing team for that, right? So what I'm trying to point out is here we got the payload at land. Why? Because we launched from Wayanad. But is that the same situation we have when we launched from Kochi? Not at all. Let's see what happens. So we came back. So we are excited about this, our annual tech fest, and we wanted to, launch this balloon. And when we were looking at the prediction, so this is a prediction. You could check the URL if you guys are interested in this kind of stuff. So this predictor told us that we were going way into the ocean, right? So that ain't good. So what do we do? So we really need to find a method to get us on land. See, if I'm going to launch my payload and it's going to end up in the ocean, and since it's unguided, it's going to fall into the ocean. I'm going to have to call the Navy and all that sort of stuff to go get it, right? So what do I do? So we need to think about a method wherein we can make this payload land on land. If that makes sense. So why is it drifting into the ocean? Well, so this image should explain that. So this is also a really interesting site. You guys could check it. Check it out, nullschool.net, right? And here you see all the winds are westward. And let's check the speed, 75 kilometers per hour at an altitude of around 10 to 12 kilometers. Now this is really fast. And our payload is hurtling towards the ocean. So we have to do something to stop it. So let's look into what we did. So the fundamental idea was, okay, we don't want to land in the ocean, right? So if you're going to the ocean, just make the payload land. So that is the, the most naive thing you could think of. And that's what we did, yeah? So what did we do? So it can be seen here. What we did was a technique called geofencing, right? So geofencing, basically what it did is, it ensured that you could, cut it off before we went to the ocean. So that was the plan. So if there's time, I would like to go into the details of geofencing as to how we did it. But since we'll be focusing more on the electronics part today, I think we leave the algorithms out. So let's just discuss what happened in a very small manner. So basically you're here, you're in the Kerala side of things, and your balloon is going here, right? And the minute you reach this imaginary line called the geofence, what happens is, this fuse wire, what you see here is a slow motion shot of the fuse wire being burned. So you have a battery that shorts all of its current across this wire, right? And it burns this critical wire. So what that does, it separates the balloon from the payload, and immediately the parachutes are out and we are coming to the ground, right? So that's what's happening. So that's the whole idea. So basically, what did I say? We're going to deploy a state separation mechanism with a fuse wire, right? It burns and we are coming down. So we don't end up in the ocean. Now, there's another problem with that, and I'll get to that shortly. Here it is, the big problem. So there might be a small lag in the video, the slides coming over, but this is what our primary issue was. So I think the next slide shows it a bit more well. So on the day of the launch, we are expecting strong winds to the ocean. However, that day's prediction showed us that if you're going to cut right here where this red line is, use that as the geofence, what's going to happen is you're going to cut off far earlier than before you reach your highest altitude. Meaning you may encounter the geofence before you reach your target altitude. So what am I trying to say? Our payload rises, it's going up, but the winds initially draw towards the ocean, and then at high altitudes the wind is inland, right? So you're going back inland. So this causes to encounter the geofence really early. So what we did is at the very last moment, we had to cancel this geofence idea. That is close to 10 to 15 minutes before launch. Like that was a really hectic piece of time, right? So that was the first idea. So geofencing. So we have strong westward winds. That is the first constraint, and then we have a strong westward wind, and along with that, we also have this issue of not moving. Let's see the actual design, right? This should look really scary, at least for few guys not from electronics. So I don't know if that slide has come across yet, but so the actual design included a PCB, right? PCB is printed circuit board for those from different backgrounds, right? So what this did was it basically it controlled the entire PCB, entire. Let's do it magic. That is, and we're back in a clean state. So the moment the one without the red and blue line. And so this PCB has 3 cores, core 1, core 2, sorry, that was core, this is core 2 and core 3, right? So now we have a clean slate. What are these 3 microcontrollers? So I'm sure most of you know what microcontrollers. This, all the processing, the communication, all that stuff happened right here. So how do we do that? Okay, so go into the details of what each core did. So basically, we have a lot of things to do. So one, we need to communicate, right? We need to tell, okay, this is where I am, mimicking the radio sonic, right? And then that's done by this core here, okay, core 1. So the next being core 2. Core 2 did logging data. All this data, temperature, pressure, all that. The next thing is, so he is a really important core. So what this core is, it is basically controlling descent sequence. So I'll discuss the descent sequence if we have time, but right now let's move on to how we design it. So a few magic quotes later, we are here and we have our final PCB, right? So this is the PCB we got from. It's double layered PCB, meaning it has tracks on both sides. Okay, so it's having a green mask. It looks really neat. At least that's what I think. And so let's see what. I know this may look a bit complicated because you didn't design it. So let's see what happens. So we have 2 sections here. So this is basically where your voltage goes in, and you have another section here where you have a backup battery source. You have 3 cores. You have 3 cores which should hold your all the processing and things like that, and you have I/O ports. So now these I/O ports are used to hold like sensors and say your antenna, your power booster, things like that, right? So now let's go into a bit detail. So this is solved. Like this took quite a while soldering, and what's on here. So we need to get you acquainted with PCB, right? So you have a power module here. I'll discuss the power thing in a moment. And you have 3 cores, and you have something interesting down here. So what is actually your programmable modes? Like imagine you have a switch which you can use to program. For example, when you're testing, you need lights such as this one to glow. But just before launch time, you don't need light. However, you have to change. So what we did is we added a number of modes. To be precise, 4 modes, right? 4 modes to give an idea of what we want to do. Say a power saving mode. So this can be programmed without changing the program. I hope I was clear. So basically, I say if switch 4 was on, I'm going to say switch turn on the power mode, or say use an alternate battery source. So that is why this switch was used. That is the of what we did with PCB. So we have I/O ports for input-output operations, things like that. What do I mean by I/O? Input-output. we have external peripherals. What are they? They are your units such as your power booster, your antenna, things like that. Okay. Now let's move into the details. So now, as I told you, we needed a portable receiver, right? So this posed a few issues. So I know my spelling is really bad. Yeah. So if you, those of you who know the Arduino board will notice that this is shaped just like the Arduino board, and it is. So what we wanted to do is we wanted to make portable receivers, meaning you could just plug in to your laptop and get data from this radio soundwave. Now that was something that was an issue with even the raw radio soundwave, meaning the commercial radio soundwave, right? So that's something what we wanted to do. So this was shaped, as you can see, just like an Arduino board. Those of you with good net connection should be able to see the slides changing. So now what's it's right? Just been going to see. We had a lot of now what's stop. Why? Well, simply because this we were running at the edge of these chips capability, right? So this was basically Atmega 328, the board, the same chip you find on the Arduino Uno, the same microcontroller you use on your Arduino Uno, right? So what happens is they often get hanged, and this could also be due to low temperatures. Like we are going to 100,000 feet and beyond, right? So that's really cold, and most electronics is not going to function there properly. So that was a big no-no. So what did we do? So we had to figure out a way wherein we could, communicate with the to reset themselves at a given interval, right? So all the boards were in a cyclic reset setup, right? So they used to reset themselves as and when necessary. So we didn't. What we did here was telling, after say 5 minutes, he resets the first core, resets the second core. The second core resets the third core. So in case any of them gets hanged, so what am I talking about? Like you're getting this data, it gets too cold, and say your system shuts down, right? You want it to be able to come up again, right? You could have gone into any number of faults in the code, some bugs, things like that. You want to get out of them. So you're using a watchdog. So those of you we learned this in class as well. So let's just continue with our this session. So now, how are we managing power? LiPo batteries don't work at these altitudes. That's a big issue. See, the batteries we sort of use are LiPo batteries, lithium polymer batteries, and they don't work at negative temperatures. Now, that's a big issue. So what do we do about it? We make good insulation. We have heat management. So that is how we use LiPo batteries, although we were going to the edge of space, right? So now, how are we managing power? So if you think about it, our flight time could be, say, 5 hours, right? So if you're going to for a flight time of 5 hours and your batteries don't last, you're not going to get data. No data means you cannot retrieve the payload. What's the idea? You send the payload, get the coordinates, go and get the payload, right? So if your batteries are down, you're not going to get transmissions. You're not going to get the data. So that was a big issue. So what did we think of? So now let's go to that circuit I was talking about. So as you can see, that is the power input, right? So you plug in your battery here and you plug in your battery here. So what's going to happen there is one is a backup source. So this relay, so for those of you who don't know what a relay is a device that can switch, it acts like a switch for higher powers, like for higher power meaning more currents, greater amount of current passing through it. So this relay is going to switch from a backup power source and a main power source. So why is this essential? So how is this activated? So basically what I want to do is, I say that, say, my flight time is not going to exceed 5 hours. So after 5 hours, say the payload has gone up and the battery died for some reason and we are having no charge, no transmissions. But I want to ensure that I can still find it. That too after we land. How do I do this? Once we land, we want a new battery to start up. How do we do that? So that's the interesting bit here. So what we did was, we had this backup. This core 2 was having minimal operations, right? He used very little power. So what did we do? We told him to run on the backup source. So he's not going to drain the charge, right? charge is drained by the transmission system. So we'll get to that in a moment, right? So the transmission system is giving off a lot of energy, like it's consuming a lot of power as well. So we want to save power. The idea being our payload goes up, loses charge, and is dead, right? And 5 hours later, we want the system to come back to life. How do we do that? We do that with the backup source. So after 5 years, an RTC module, what is an RTC module? Real-time clock, right? This RTC module starts up and tells this core, okay, the core number 2, it tells it, okay, start up your boot the system. So what happens is that backup battery, which was not being used till now, suddenly powers up the entire board. And a board that was dead for say an hour or more suddenly comes back to life. And so we can tell the exact time when this backup system is going to start. So what that does is it tells us, okay, here we are. We have a Kotlin again. Although our main batteries might have died due to say longer flight time than expected, worst case, say 5+ hours, we don't have a battery. And now we can restart the system and save this essential data in such a manner, as in going off to a battery source, a backup battery. So that's the idea of backup battery. I hope I was being clear, right? So now the temperature variation. Now that was a real issue. So we had to go to say 50 kilometers and endure all the harsh environment around us while maintaining normal equipment. Like we didn't have military grade equipment. We are just a student organization. We are just a bunch of students who are interested. So we didn't have military grade equipment. All we had was, this idea. So we had to make sure our equipment worked at minus, close to minus 10, 20 degrees temperature. Actually, close to minus 60 degrees. And most of our equipment is rated only up to minus 40. So now that's a big issue. So what do? We tested using dry ice. So now dry ice, as you can see in the top left image, is really, it's all carbon dioxide. It's really cold. And by immersing our equipment in a dry ice chamber, we were able to simulate what it might be like at those altitudes. So now we had gone through many options to maintain heat. So one, we used, so if those of you who have seen our payload know that it is an ice box, right? So it's really good at keeping the temperature constant. So it prevents heat from going out and what coldness or heat from coming in. Basically the same thing. Yeah. So what did we do? We used inefficiency. Now for an electronics person, for an engineer for that matter, energy loss is a big deal. And for electronics, energy loss in terms of heat is bad, right? That's what we are taught. We use that to our advantage. We use devices like the, say, 7805. So for those of you who don't know, it's a 5-volt regulator. You can please Google it. So we use the 7805 and IC for regulating 5 volts. That's a no-no, big no-no, because in terms of efficiency, right? You have devices such as buck and boost that can work at 95% efficiency. And we're not using that. No. We're using the 7805, which has a really poor efficiency. Why? So that we can generate more heat. Right? This is one place where things like that do good. So we are using thermal insulation, number one, using an ice box. Number two, we are using inefficient chips, and we are using heat sink to boost the internal temperature. So let's see what that did. So here are our graphs. Okay, so it's really easy. So let's just figure it out. So in the left, right, in the left you see a graph that shows internal temperature, and in the right you see a graph showing external temperature. So this is actually from our onboard sensors, right? And you will notice that internally our temperatures went down just to close to zero, right? We never went, the internal temperature, the electronics, just faced sub-zero temperatures, although they were capable of withstanding up to minus 40 according to the data sheets, right? So however, the external temperature went as low as, no, it wasn't minus 20, it was minus 40, somewhere close to minus 50 actually. So what's with that huge dip here? That's where our sensor failed due to the low temperatures, right? So you see this rectangular portion here, our sensor actually failed during the descent. Now, one more interesting thing that you can make out through these graphs is a small hole in the graphs here, right? So at the very bottom, you have the, altitude versus you have an altitude graph here. And you notice that at close to 50,000 feet, sorry, at close to 50,000 feet, what happened was we actually lost connection, right? So what happened is we have some sort of, so we still don't know to date what happened there, but it looks like a system shutdown. However, the watchdog mechanism I told you about resets and to make sure everything boots from a start in the proper boot up sequence, right? So I'm not going to go into those details, but you guys can get an idea of what we went through. We went through temperatures as close as as cold as minus 50, and at maximum altitude close to 55,000 kilometers. Sorry, 50 kilometers, 55 kilometers, right? So this is something we discussed, the hanging controller. We used a watchdog system to rectify. I repeated, I told that too early, I guess. So I think that, I hope that's clear. Now, the interesting bit, communication. So interesting, meaning it's something we didn't know and you wanted to find out. Like, how are you going to communicate over kilometers, 60 kilometers? Oh, that's a really big number. So we want to communicate this far. So what is our mode of communication? So we chose the UHF mode of communication. Actually, we wanted to first find out what happens, right? So we have an issue with the ionosphere here. So you can see the ionosphere. So that reflects waves. So if our payload goes, say, in the ionosphere region, we are not going to be able to communicate. So what do we do? What do we do? We use very high frequency signals, not as in VHF. So we chose 433 megahertz for a number of reasons, right? So basically what we did is 433 megahertz was our frequency of choice for communication with this payload. So the first payload had only a one-way communication, meaning the payload talks to us. We don't have the authority or the capability to speak or command the payload. So now let's dive into the communication. So this really good picture you see taken here at the top left is the PCB we are all really proud of, right? And this is the LoRa module. It's a communication module, which for very small ranges. It's not meant for long ranges, right? So what this does is it helps you transmit signals at 433 megahertz. So now, say close to 1 kilometer, that's the maximum you can get through this module. So what do? We had a really good team for all this. We had ham operators, one from our own college, CUSAT, who helped us out with this. So what happened here is we wanted to say, basically the issue is it's not in range. We just get say 100 milliwatt output. Now this is a pretty good signal, but not for long range. So what did we do? We wanted to boost the signal. So what you see here is an SMA connector. So this is an SMA connector down here, and now we're going to connect this SMA connector to a power amplifier module. So this power amplifier module, what it's doing is it's going to boost the signal to from 100 milliwatt to 3 watt. Now that's really powerful, right? And we were getting range practically close to 60 kilometers. Now I think that's pretty good for a BTech student, group of BTech students, right? So now, what about the output? So the output is going to a set of antennas. So these are two antenna designs, number 1 and number 2. So the first is a right circular polarized antenna. You guys can Google that up. I'm not going to those details. And the second is a more simple, really simple design, ground plane antenna, right? So this ground plane antenna and these antennas were what we used. You see this big disc here, it's just a reflector. So why did we use a reflector? So possibly because all we wanted to do was point the signal towards Earth, right? So you have to imagine this. We don't want a 3D signal exactly. We want the signal to be pointed right down to our ground station or to wherever our portable receivers are. So that's what we want. So we wanted to reflect the signal down to Earth. So that's what we did here. And even this angle is also meant to direct signals like this downwards. Actually, this antenna was supposed to be inverted. So that's the basic idea here, right? So you have the signal in this direction, right, in 3D, right? So what is happening is that causes you to get this data, get data down. So we don't want the signal to go up into space. It's useless. We need the signal down here. So now combating interference. So this is really interesting, it made us go crazy. Couple of nights actually. So we are working really hard to get this communication system up and running, and all of a sudden it looks like we are living in a haunted house, right? Suddenly LEDs, which are not at all connected to a battery source, start lighting up. Now that's really bad. That's when you think you have totally lost it, right? So what happened here? So I'm sure that most of you know this bit of circuitry right here, and we have been taught, it helps in removing the AC part of the signal, right? So, so okay, so that's something I have never personally experienced. So why do you need to remove AC? What's the big deal with it? How does the AC get there in the first place? Oh, we found that the hard way. What happened actually was we were trying to transmit these signals really powerfully, and this signal started, because of the high frequency, started interfering with the microcontroller's logic. It started getting into the power supply, and everything went crazy. What was the problem? A small capacitor, right? So this was a power amplifier module which generated this, boosted the signal to 3 watt, and it was really messing things up. What was the problem? This small little capacitor right here. Uh, so that capacitor is called a decoupling capacitor. It basically removes the AC. What was the AC in this situation? It was the very signal we were trying to communicate. The signal we were trying to send to the receiver was interfering with our control system, right? So that was an issue. So that is what we faced. So that was a really, it was horrible. Trust me, it was horrible. So because we had no idea what was going on, and a capacitor solved a few nights, a few sleepless nights, right? That is really. So I actually always thought you could just take out a capacitor when you want. Now, because most of the time capacitors, we don't see them responding. Like in the labs, you can try removing a capacitor, and very rarely does it create a big change in the output. So I thought capacitors were useless up and until this point. Oh, they're great, trust me. So now let's get into the communication mode. So basically, we needed 2 modes of communication, 1 and 2. So why in the first place? We have such a good system that can communicate over, say, 60 kilometers. Now that's pretty good, So why this extra communication mode? So basically, this works great when you're really high, say about 50, 60 kilometers. Say 30 kilometers. You're there, you're good, right? You have a line of sight. This is the best for line of sight. You have a direct wave reaching your payload, everything's good. But the minute we start descending, right, when we want to retrieve it, we need to know where it is. So supposing we land, say, right about here, and definitely there are going to be obstacles in the way, right? So now that's a big issue. Why? We are not going to get the signal. So that's when UHF meaning ultra high frequency, 433 megahertz, did not do the job. What did we do? We resorted to another bit of technology, GSM. So I'm sure most of you know. So basically, you are just sending an SMS to your phone with the GPS coordinates. So now this module is the SIM808 module. It also has an inbuilt GPS, right, and a GSM module. So it has them both, right? So you can you can send an SMS with redundancy. What do I mean by redundancy? We only have a GPS module in our primary system. So this GPS system is just a backup, right? So it is there in the SIM808 module and will send us the coordinates when we lose UHF communication, meaning ultra high frequency communication, meaning line of sight communication. When we don't have the payload in line of sight with our receivers, we get an SMS. Now that's great. But the issue is SMS doesn't work at high altitudes. Like your cellular network is say close to 3 kilometers, and that's about it. So above 3 kilometers, no geo, nothing is range there, right? So there we use UHF. And when we are at really low altitudes, what do? We use the GSM network. Now that's basically the idea. So that's pretty cool. So although I say so myself, that is a good thing. And that wasn't our idea. It was a collective idea. So that was really great. And now the receiving team. So I've been talking about a receiver. And unlike the previous cases, what we did was we needed portable receivers. So you can see many of our team members, part of the retrieval team. So let's just break this down a bit. So you see, this is what we received. So this is the Arduino IDE. And like I said, our big innovation here was instead of a big setup with signal processing and all that stuff, we could plug into your laptop, open the Arduino IDE, and get data from your radio socket, which is over 60 kilometers away, right? So that was cool. And here you can see the strength, the signal strength in dB, okay, in dBm, sorry. And these are pretty good signal strengths. So negative signals are what you get, right? So this is the closer to you are to zero, the stronger the signal, right? So minus 30 dB it's an okay signal, right? So now let's see the antenna. So this is the circular polarized antennas I was talking about, right-hand circular polarized antennas. And what you see here is that you remember the schematic I showed you up top of a device shaped like an Arduino, which you just plug into your Arduino board and you get the data. So this was all that the receiver system was. And here Aftab and Anis are getting the data from the payload. So this was ground testing, and so we had number of receiving teams which were going. So I just want to point out how innovative that shield thingy was. Like if you look here, you can see lot of wires. So in our first learns from Payload, we used this to receive our data. And every time we moved, so basically our receivers are mobile, as in we are moving. Like these receivers are usually kept in cars, right? So we are mobile and we are trying to get this data. And now loose wires, a big problem. So this shield basically was just plug in. You have no loose connections, and plug in and you get this data. And so this is the data we got. And in the bottom left corner, you can see the actual thing happening. So this is a snapshot from one of the retrieval vehicles. So I think you get an idea. So we have an SMS system which gives you data below 3 kilometers, and RF communication, line of sight communication above 3 kilometers. So now, just to give you a glimpse of the sensors, I've not named them. So we use the MS5607. Now, trust me, finding sensors is hard because most sensors are rated for below minus 40 degrees. So if you're going high and above, you really need good sensors. And sensors need to be exposed to the atmosphere. So it's not like you can keep them within your insulated system. Like if you keep us insulated within the insulators, you're not going to get the right pressure. If I keep my pressure sensor inside the box and seal the box such that no temperature comes in, the pressure is also not going to get in, right? So that's an issue. So selecting your sensors was quite a task. Like, so we had to look into sensors that could actually, deal with these temperatures. Same goes for pressure, altitude. So pressure, so these both are nearly the same. Humidity, internal external temperature, ozone, things like that. So that was what our circuit was all about. So now I just want to, so I'm about to close here in 10 minutes. So basically what we're going to do is, let's go through what all we went through. So our design objective. So I told you a big story. Now let's see where we reached, right? So we wanted to collect essential atmospheric data. Did we do that? Yes. We got this data, and I forgot to mention, we logged this data, right? We put this data onto an SD card. So we transmit only the coordinates, the 3D fixed location. So that the fourth point done. So what that does is we get the altitude, the latitude, and the longitude. The data essential to fix a point in 3D space. Basically, in layman's terms, go get the payload, right? So that's what helped us, what that could did. So we check thermal insulation using inefficient voltage regulators, or really inefficient transmitter, not necessarily inefficient. Most transmitters, when they transmit this power, they always have a lot of waste. And we were able to log essential data into your device. So I told all that. What I did mention was rapid descent. I'll get there, and the descent sequence. So geofencing, I mentioned that, and then get footage. So now a big issue with getting footage is, the payload is always spinning. How do you get data in an effective manner, right? So we are nearing the end. So if you guys have doubts, please put that down in the chat box. I'll go through them in a moment. Yeah. So where was I? Yeah, the footage. So if the camera is spinning, it's not going to look at all good. So that's pretty clear. So we need some sort of stabilization. So we didn't want to design it. We just used the GoPro Max, so GoPro Fusion 360. So what that did was, it was a 360 camera, right? It captured and it does image stabilization. So that was, so I'm going to end at that. So you guys can Google that if you're interested. However, we are looking at things where we can change, right? Now, design constraints. So we have a power issue, wherein what happens if our batteries run out? We have a communication issue, communicating beyond 60 kilometers and at high altitudes and at low altitudes. A big issue. We solved those issues. So these are all, I'm just summarizing what we did so far. Strong westward wind. So that's causing us to end up in the ocean. I showed you the flaws with our system as well. So a hanging controller, the watchdog system, basically, like how it is going to, prevent us from, getting hung up in a place where then it's a hung controller does nothing, right? It's dead. It's just wasting your battery. It still takes power, by the way, but it's not doing anything. So that's really, really annoying. You're wasting power with no data. So processing requirement for data sampling. So now this is an issue I didn't mention. So basically, why did we need 3 cores? Couldn't we make this one? No, for 2 reasons, right? So most sensors have a very slow sampling rate. Sampling rate meaning as how fast it can take data. So you can take data from a sensor, say every 3 seconds or every 1 second. So if I was going to run this as my main code, I'm going to slow down my entire code. Now that's also a big no. So we need to be fast. Our processors need to run fast enough to get this data, do the processing requirements, especially in the descent sequence. I'll get to that in a moment, right? And that's where processing requires data sampling was an issue. So we had to keep a dedicated chip to get sensor data. So the third core was having your sole responsibility of collecting data and logging it. So you have file input IO, input and output operations. Basically, that's again a slow process, like where you take data and store it in a file. Now that's slow. Take data from a sensor, that's slow. So we kept that separate. So now we also showed you the portable receiver, how we could receive data. The antenna is connected to a portable receiver, which is connected to your laptop. You open the Arduino and you get the data. And we also showed you how we dealt with the interference, right? So now let's see where we can improve. So we're looking for ideas in this domain, geofencing. So I showed you, for those of you who joined late, basically the wind turns and is unpredictable. So we need a technique to make sure that our geofence does not deploy too early. Right? I hope I'm being clear. Number 2, it would be great if we could actually figure out if the balloon bursts. Right? So if the balloon bursts, we need to know. We could transmit that signal back. But creating such, even if you're using machine learning or AI for that, we have really poor data sets, available data sets to get this done. So that's also a scope of research, like where we could actually do this. Now, an altitude hold algorithm. So now you guys must be wondering what that is. So wouldn't it be great if we could make the payload, I mean the balloon and all that stuff, stay at that altitude for prolonged periods of time, say weeks? That would be cool, wouldn't it? So for that, we need to know why a balloon breaks. So with that, I'm just going to skip over the rest of the points. You guys could just read through it. So I just want to show you how a balloon bursts. Okay. Uh, I hope I'm back. I seem to have an issue. I seem to be having an issue. I'm sorry. So please do tell me when I can be seen again. I believe you can see me now. Yeah. So those were the design objectives. So I just want to quickly go to the end. So now this is what our payload looked like. So many of you might not have seen what the payload looks like from inside, right? So I'm not going to the descent sequence. So I'll just briefly, because I'm unable to switch out from this and it's turning off the screen share. Right. So basically what I'm doing is I have my power amplifier module way at the bottom. Right. So this is what you see here. So why we did this was to prevent interference. So we wanted to completely isolate, totally isolate our control system, our PCB, from the main system, meaning the communication system. So this is going to create a lot of interference. So that's what we did there. So then here came our PCB, right? So our PCB came on top, insulated by some sort of cladding, a dielectric, to prevent signals from coming here. And although that isn't the technical way of doing things, uh, it kind of worked. So you might notice that this is not the PCB I showed you. So we don't have photos of the other PCB due to the lockdown. We couldn't find any. So this is what our previous PCB looked like. So you have the power amplifier at the bottom, you have a PCB on top, and just over that you have your batteries, right? We used around 7,000 mAh of batteries in total, meaning we could get a flight time of definitely close to an hour. Our power input was, we used power close to a few, around, around just 2 to 3 amperes, the max during transmission, right? Most of that power was taken during the transmission. And it was interesting to note that a relay could often take more power than the actual control system, right? That is really sad. So now, at the very top, we have this new set of antennas. So what are they? You remember the GPS and GSM thing I told you about? So this is the GPS antenna, and this is the GSM antenna. So that's basically at the very top to ensure that we get satellites. So basically, you need 6 satellites to get the GPS log. So, so that's why we kept it at the very top, right? So that comes to about the end. So I have 4 minutes, I think, and in that, I'd just like to tell you about our descent sequence. So it was really important that we get our payload down safely, right? So this balloon goes up and pops, right? So how do we get it back safely? So if I immediately deploy a parachute, say at my max altitude, 30 kilometers, okay, I deploy my parachute, what is going to happen is this parachute is going to come down really slow, as intended, yeah. But the winds are also going to add to the drift, right? Your payload is going to drift even more and more. So basically, that's not good, right? So we need to come down really fast. So what do we do? So our initial thought was don't deploy the chute, wait for the payload to come down, say to 1 kilometer, and then deploy the parachute. So you're basically free falling really fast, and your payload, you deploy a parachute 1 kilometer, it slows down, it lands all slow. But the basic issue was, you remember the thing I told you about the antennas we designed? It was directional, meaning it did not give signal upwards. So if we were free falling, we could very well assume that the payload is going to spin, right? So spinning payload means a spinning signal. So our signal is going to be spin. So you get what I'm trying to say, right? So we're going to topple, and the signal is going to go everywhere, right? It's going to be haywire, and then we won't get the signal. So we need a way to orient. We need to do a maneuver to orient this payload in the up top down direction, right? So we need to. So how do we do that? So a very clever idea we got. We say it's clever. Yeah, you can have your opinions. So our payload, instead of deploying a big chute and slowing down, we deployed just a small chute, right? So I know it looks really bad, but basically that's supposed to be a small chute. So what chute meaning parachute? So what this did is this small parachute is really small and does not reduce the speed significantly. However, it orients the antenna downwards. Now this was something we really needed to establish good communication. I hope I'm being clear. The other advantage was it helped us in reducing the terminal velocity. Terminal velocity, Google it. So what's that about is we want to orient the antennas downwards so we get our signal down, while at the same time we want to make sure that we are coming down in a controlled manner and that our payload stays in one piece, right? So that was the basic idea. Now at 1 kilometer, what do we do? When we detect the altimeter meaning the instrument that measures the altitude, detects 1 kilometer, what we do is we immediately deploy the main chutes, right? So our main chutes are deployed close to 1 kilometer, and that ensures that we come down really slow. However, we removed this final feature from our final launch because we saw a safety risk. Just imagine, our rogue chute meaning it's coming really fast, say 50, 60 kilometers per hour, you're coming down, and suddenly, for some crazy reason, what if our controllers could not deploy the main chute? Worst case scenario, we could kill somebody. So what we did is we didn't do this. We took the risk. But this is something we had programmed and we had ready and on standby. So that about sums it. I know I've been really rushing through things, and I'll be willing to explain things if anybody is genuinely interested, even in person. That's fine. So now another thing I would like to do is answer your questions. So if any of you have any questions, I'd like to answer that right now. So you could answer into the chat box. So I really thank you guys for
Thank you.
being so patient. Thank you.
So thank you, Timothy. We will go ahead and take some time for the questions now. Just a reminder, please be sure to type your questions into the question box in your control panel. Or if you feel, you can ask him directly by unmuting your mic.
So just to clarify, in case any of you had asked questions earlier, my chat screen is apparently refreshed and I'm having no messages right now. So you either ask me a question personally or through this chat box now. Any questions? Either you're all sleeping or you guys understood everything, or I was really bad.
Go ahead, guys. Ask some questions.
Yeah, I see a hi from Edwin. You guys can feel. Yeah.
Hi, Timothy.
Hi, ma'am.
I heard you mentioning about omnidirectional antennas and thereafter directional antennas as well. I just couldn't get it. What was exactly the antenna you used?
So we used in the first launch at Wayanad, we used the ground plane antenna. So what we did there was so that is giving you direction only in I don't know how to say it. Or it doesn't give you signal behind the antenna, right? So that was what I was trying to portray there.
Yeah.
And in the second case, we used a right-hand polarized circular antenna. So what that is, we used a reflector to make sure the signal was more or less downwards.
Okay. Were these antennas planar antennas? Okay, maybe we'll discuss later, Timothy. Next semester. Next semester.
So
okay.
Yeah.
Thank you, Timothy. Well done, well done. Good job. Thank you.
Hi, Timothy.
Hi.
Hello.
Yeah.
Can you hear me?
Yeah. Fine.
When you deployed the payload, did you have any kind of interference from any other sources, like sources which you didn't anticipate from in the atmosphere?
Yeah, that's actually what we did was answering the question. No, we didn't have any other interference. However, we did get some garbage values. I think that's due to the long distances. But other than that, we didn't have any interference because we were using the 433 megahertz band. It falls within the ham band. So this band prevents like very few people use it. And at that moment, we had ham operators with us, and they made sure that frequency was clear and no communication was taking place at that time. And
okay,
also,
so
we were we were transmitting at really high power, 3 watts, right?
how much watts?
Close to 3 watts. 3 watts.
3 watts. Okay.
Our output power, and that actually nullified if any external signal. At least that's what we hope, and we didn't find any interference at that time. Yeah.
Okay, that's good. So you only transmitted the coordinates of the payload, right?
We transmitted coordinates as well as the altitude, like just to keep a track of how high we were.
Okay, so it was not required that you should have a high bit rate transmission, right?
No,
you only needed low data.
Yeah. We also wanted to save power, so we transmitted only once in a few seconds. Like we actually send over 100 packets of data in in intervals of 30 to 40 seconds.
Okay. And what antenna did you use as a receiver? Monopole antenna, right?
we use the same antenna we use at the transmitter.
Okay.
First we use the ground plane antenna. Second place we use the antenna I showed you. Yeah.
Okay. 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 Thank you.
Anybody else? So I know many of our team members were also in this group. So those guys did a fantastic job, and that's why Mission 100K Feet did what it did. And so did the faculty. We had a lot of support from them. So I hope you guys enjoyed it.